Hi everyone, this is just a quick tutorial that's meant to sort of take you through the highlights of the development of the modern atomic theory. Really, I feel that the emphasis on this topic is understanding the progression in scientific reasoning from the initial conception of what modern scientists believe the atom to be like compared to where we are in present day and what we believe about the atom. So I would suggest don't get too bogged down with historical dates and facts and figures, though you should have some awareness of what scientists were involved, you should have some awareness of their experimental setups, and what the key conclusions were in each of their works so that we can sort of piece together, again, that progression between the initial modern atomic theory to where we are in present day. If we consider what most people believe the atom to look like, it would look a lot like the majority of the pictures on this page. Normally this picture right here, which most people associate with Jimmy Neutron. Again, most people are aware that atoms are particles that are involved in chemistry. They're aware that there's some sort of inner core with things sort of zipping around on the outside, but obviously we don't necessarily believe that the atom is exactly like this now, and certainly the atom initially began looking quite different in the mind's eye of scientists. Initially, all right, the first sort of linchpin, if you will, in the atomic theory was actually contributed by John Dalton. And Dalton observed chemical reactions, mostly reactions that were in the gas phase, and his observations led him to four main postulates, all right, which again I'm not going to necessarily read them to you word for word here, but essentially the main idea behind Dalton's work is, well, okay, all matter must be composed of atoms. When I consider an element, all of the atoms within the element are exactly the same as each other, but if I'm considering two different elements, then the atoms of each of those elements must be different from each other. There was also a notion that, okay, atoms cannot be created or destroyed, what we know of as the law of conservation of mass, but Dalton added to this by also saying, well, the atoms of one element cannot be converted or changed into atoms of a different element by normal chemical reactions. And then also, Dalton was aware of the existence of compounds, and so Dalton also was able to reason out, well, compounds must be combinations of atoms, and if I have a compound, then regardless of the sample, then the compound must be made up of a specific ratio of these atoms. Now, even though it's nice to see Dalton's atomic theory in a nice tabular form like this, the main conclusion that we're concerned with is, okay, based on what Dalton knew, if someone were to ask Dalton what the atom looked like, he more than likely would have answered something like this. Basically just the sphere, because he simply did not have evidence of the atom being composed of any smaller particles. He believed the atom to be the fundamental particle of matter. Basically, nothing could be done to divide the atom any further. Now, obviously, we're aware that that's not true now. All right, but how we got there, again, depends on more of the work associated with these scientists that contributed to the development of the atomic theory. Now, from here, from Dalton's conception of this spherical particle that he called the atom, we have the work of Thomson. Now, Thomson carried out this cathode ray experiment. Now, the important sort of observations to note about the cathode ray experiment is that these cathode ray tubes are actually filled with a sample of a gaseous element. All right, they're also coated with a fluorescent coating. Okay, and upon application of an electrical charge via the electrodes at the ends of the tube, with one electrode being negatively charged, which we call the cathode, and the other being positively charged, which we call the anode, the result was that we got a beam, a particle beam, that traveled from one end of the tube to the other, from the negative electrode to the positive electrode. So based on this observation alone, then Thomson was able to reason out that these particles must have some sort of negative charge. Now, he was able to further corroborate that by the use of a magnet. Basically, he took a magnet and he oriented the positive end of the magnet towards the cathode ray tube. And if we take a look at the behavior of the particle beam, then basically we can see that the particles that make up the beam curve towards the positive end of the magnet. Now, Thomson was aware of the general behavior of charged particles. Basically, particles that have the same charge, so two positive particles or two negative particles, they will repel each other. And he also was aware that if I have a positive particle and a negative particle, then basically these particles would attract each other. And so, based on this evidence, he was able to conclude that basically matter, or specifically atoms, must have some sort of negatively charged particle. And it's been said that basically Thomson tested a number of elements. And so the behavior was the same, regardless of the gaseous element that he put in the cathode ray tube. And so, based on his work, he was able to conclude qualitatively that all atoms must have negatively charged electrons. But he also knew that atoms are neutral. Now, if atoms are neutral, then that means that all atoms must also contain an equal amount of positive charge. So he was able to understand, okay, there must be positive charges and negative charges within the atom. He also was able to make a quantitative measurement of the electron, of this negatively charged particle. He was able to determine what we call the electron's mass to charge ratio. Again, I'll include the value here as a point of reference, but basically it's the following value, negative 1.76 times 10 to the 8th coulombs per gram. Again, don't worry about memorizing that or being able to do calculations with it. But the reason I include it is because in the next slide we'll actually discuss a little bit about how that particular number was used to further characterize the atom, and especially the electrons within the atom. Now, in addition, all right, Thomson then conceived of an update to Dalton's picture of the atom. He figured, well, if there are positive and negative charges contained within the atom, the simplest model that he could reason out was that there must be these negative particles, these negative electrons, randomly dispersed within a sea of positively charged matter, which he considered to be the rest of the atom. So when we consider that, all right, we have to think about, okay, well, what else can we know about this electron? What else can we glean from scientific evidence about the electron? And that's where Millikan actually comes in. Millikan was able to, via this experiment here, it's his famous oil drop experiment, he was able to determine the mass and the charge of the electron separately. So we know that Thomson was able to determine the mass to charge ratio, so the ratio of the two values. Millikan was able to actually separately determine each value, and the way that he did that was by this experiment in which he took a spray of oil, all right, bombarded the oil with X-rays. That's what this portion of the diagram represents, an X-ray source bombarding the oil droplets, and that imparted a charge, all right, and this charged droplet would then be forced to fall down towards the bottom of this compartment via gravity. But to counteract this effect, basically Millikan used these charged electrical plates, all right, to actually have an effect on the droplet's motion by, again, using that charge and the law of repulsion and attraction of charges to each other to be able to affect the rate of fall of the oil droplet. By doing this, he was able to specifically come up with the mass of the electron, which ended up being about 9.1 times 10 to the negative 28th grams. He was also able to determine the charge. So that's the mass of the electron. The charge of the electron was determined to be about 1.6 times 10 to the negative 19th, and the unit of charge is coulombs. Again, the exact numbers aren't necessarily something you have to memorize. If you need to do some sort of calculation with them, they'd be provided to you. But again, the important thing is to understand that Millikan's work built on Thomson's by further characterizing the electron and allowing us to understand more about its physical properties. But in terms of the further development of the atomic theory, then we need to next consider Rutherford. Now, as it turns out, Rutherford was one of many scientists that actually discovered radioactivity and also was able to characterize the different types of radioactivity. He then selected one of these types of radioactive particles, namely these alpha particles. And he decided, okay, I'm going to take these alpha particles and I'm going to verify Thomson's model. And essentially the way he did this is he decided, I'm going to take atoms. Specifically, he selected gold atoms. And I'm going to actually shoot these positively charged alpha particles at these gold atoms. And if Thomson's model is true, and these negatively charged electrons are sort of randomly spread out in this sort of diffuse sea of positive charge, then basically these alpha particles should just zip right through because there's not going to be any specific obstacle to the alpha particles as they travel through the atom's space. And so he came up with this experimental setup where he has his source of the radioactive alpha particles. Here's his gold foil, his source of gold atoms. And the alpha particles were to be shot at the gold foil, and again, assuming Thomson's model would be correct, then he should have gotten straight passage of the alpha particles through the gold foil, which he detected via the use of this fluorescent screen. All right, but as it turns out, there were some deflections of these alpha particles. Not only were there some deflections, the deflections in some cases were extremely severe. So Rutherford asked himself, well, what's the source of these positive alpha particles being deflected so widely from their anticipated angle? And so once again, it comes down to understanding the fundamental behavior of charged particles. If positively charged particles are being deflected significantly, then the source of that repulsion also has to be positive. And so Rutherford envisioned the atom in such a way that, okay, there must be some big concentration of positive charge in the center of the atom. All right, so this dense area of positive charge is what eventually we came to know as the nucleus, with the rest of the atom being made up of essentially empty space, with the electron sort of zipping around within that empty space through to the outer boundary of the atom. And so thinking where that puts us in terms of the different models of the atom, well, that puts us here. All right, now obviously we know that we also have the Bohr model and eventually the quantum mechanical model. We will review those models in greater detail towards the end of the year, closer to the AP exam, but at least you have some idea and some background as to how the prior three models actually came about. Please respond to the questions that are attached to this tutorial. We'll discuss in class tomorrow. and we'll continue with Chapter 2. And I'll see you guys tomorrow.